Okay, I know you just can't stop talking about Redis, but we do have some speakers we got to get to here. So I'm going to go ahead and get started. Our next speaker, our first of our community talks, is Jon Hyman. He's the CTO and co-founder of Braze. Let's give a big round of applause to Jon.
Thank you so much, Dave. Really excited to be here and talk to you all about how we use Redis at Braze to solve some of our biggest challenges. But first, I want to help you understand what Braze does. So I want to just spend a minute talking about the scale of our business, as well as the scope of all the problems that we solve. So Braze is a customer lifecycle engagement platform. Our mission is to help consumer brands use data to personalize and deliver great customer experiences through messaging. These are things like personalized emails, push notifications, in-app messages, text messages, and more. And chances are already in your pocket. So if you've ever gotten money from a friend on Venmo, withdrawn it, and seen an in-app message to withdraw that to a Venmo debit card, you've seen an in-app message by Braze. Or if you've received an email from Seamless about new restaurants you might want to order in from tonight, that was sent from Braze. Or lastly, you get a push notification from Domino's Pizza that your order's on the way. Those are all orchestrated and sent through Braze. Across our customer base, we help engage more than 1.6 billion monthly active users, and we send over 1 billion messages a day. So with this scale, I want to go through two different types of examples of problems that we ran into and how Redis was instrumental in our ability to solve them. So the first is an operational story, and it starts like most operational stories do, at 2 in the morning, waking someone up. So we got a page that our API servers were appdexing. And if you're not familiar with what an appdex monitor is, essentially it's a measure of latency and response time that was telling us that our APIs weren't responding timely enough with a good quality of service. So the on-call engineer woke up, checked our servers and CPUs and saw what was going on. We dug into all of our API servers and saw that we had a lot of high CPU utilization across them. So at Braze, we split our API fleet out into different clusters. And then we auto-scale that based on CPU utilization, because APIs are, by and large, entirely stateless. They just need to respond to requests. So what you see here is a picture from our Datadog monitoring tool, and each honeycomb here represents a different API server. This shade of coloring from green to orange talks about how much CPU is available. Good would be green. There's a lot of CPU left on the system. Orange, and that is a little bit taxed. You can see here that there's a huge patch of orange, which would indicate that some of our API servers were really taxing. So we're trying to figure out what's going on. And observability is another great thing that we think about at Braze. We want to make sure that we can monitor and figure out what's going on inside of our systems. So we used our application performance monitoring tool to inspect what the API was doing. And here's a snapshot of what it was. Maybe a bit hard to see, but you can essentially look. On the left side, you see that there's a lot of brown there, and it correlates to something called trigger payloads. We're going to get to what that is in a second, but the net of it is it's still 2 in the morning, and we've got to figure out what we're going to do. So the engineer just looks at our runbooks and says that what you should do for a CPU-related issue in the API is add more CPU. Just continue to scale up. Now, our auto-scale routine had already done this, and he just decided, well, let's just keep ratcheting it up, see if I can make it go away. Added over 70 additional servers. This is like tens of thousands of dollars of server spend a month if we kept these online, just to see if we could get this to go away. But it didn't fix the problem. On the right, what you see is a graph of all these 50x errors that our API was throwing because it was out of capacity. It's extremely spiky. They would spike up to 10%, then go down, up and down, and we couldn't really figure out what was causing that. So that's where we need to dig into what is that trigger payload thing. So it relates to Braze's in-app messaging product. So each time a customer opens a mobile app that has Braze installed in it or visits a website that we're on, that end user device is going to talk to Braze's APIs to figure out what types of in-app messages a consumer may be eligible for to receive inside the application. This is actually a fairly complicated and complex computation, because what has to happen is the API server has to look in our database to figure out what are all of the possible in-app messages the user could receive, figure out if the user is eligible to receive them based on their demographics or behavior or actions that they have taken, and then send those back down to the devices. And in doing that, there's a fair amount of CPU things that need to be done, and so we cache intermediate states of all of those different parts of that pipeline in memcached, and we would a 90-second time to live on it, so it's fairly fresh. And then the in-app messages are all returned to a client device. So when we dug into our APM tool and saw how long this was taking, we saw that when in-app messages were being requested, it would actually take up to 14 seconds for the API to figure that out and return back to the client. And this was a really high volume API. And so we saw that we were getting thousands of these requests every single time the cache would expire. 90 seconds would pass. A bunch of requests would be trying to fill that cache up because they wouldn't see anything in there. And each of those operations took 14 seconds. So we just recap all those things. We just know that this isn't going to scale. We've got a really high volume API. Every 90 seconds, cache expiry is causing all of these processes to want to refresh that cache. But refreshing the cache is very costly to do. So this is what's known as a stampeding herd problem, where you have a lot of resources that essentially all at the same time try to do one contentious thing that takes a lot of effort or may need dedicated resources there. So this just wasn't going to scale. So in order to fix this, we thought that we could use Redis and apply it to our caching in order to make this better. So what we did is we changed the way that our caching works. We thought we had a 90-second fidelity on our caching. So instead of having thousands of processes try to refill it, let's just have one of them try to refill it. And we can do that using Redis locks. So a lock in Redis is something that you can do with a set nx ex command that essentially allows you to set a key, nx if it doesn't exist, ex with an expiry. It allows it so that if you have multiple processes all make that command at the same time, only one of them will set the key and essentially take the lock, and the other ones won't, and they won't be successful. So we changed our caching logic, which used to just be check the cache, if it's not in the cache, compute the state and put it back in there, into the first thing that it does is check Redis to try to grab a lock. And if you grab that lock, that now we move to 90 seconds of expiry, even if it's in the cache or not, just go ahead and recompute it and put it back in the cache. And then because we thought, well, we've got 14 seconds of buffer time, let's just extend memcache out to 180 seconds. We're still going to be refreshing it every 90 seconds anyway, keep the same fidelity. So we rolled it out, and as soon as we did, the results were incredible, and they were very impressive. The in-app message rate of loading those into cache dropped from like 6,000 every 90 seconds to 1. And this makes a ton of sense because we were now using a global lock in order to limit what we were doing. But more impressively, the time that it took in order to do this computation wasn't actually 14 seconds. It was less than a fifth of that. It was only about 3 seconds. And the reason for that is the CPUs were so taxed that it just made it look like everything was taking so much longer because there was so much CPU, essentially, weight on the entire boxes. So when we did this, latency completely stabilized. We got rid of all those 506 errors. We scaled way back down, saving tens of thousands of dollars a month, and we're able to continue to scale our system back up. Now, the next thing that I want to talk about in this case, though, is essentially a generalization of this pattern, which is called refresh-ahead caching. And so we've since applied this in a lot of different places at Braze, where you, instead of just refreshing the cache when you need to, just refresh it ahead of when you think you're going to access it. So the way that this works is, again, when you go to fetch a cache key, the first thing you should do is go check Redis and see if you can set a lock. And if you get that lock, then recompute the state and put it in the cache. If you don't get the lock, check the cache, and if it's not in the cache, compute the state and put it back in there. And this has allowed us to scale out all of these complex computations that happen in a highly distributed nature all over the place at Braze. So there's another example that I want to walk through, which is a little bit similar to the stampeding herd issue, but is in a completely different domain. And that's how we coordinate user journeys for our customers with their messaging strategies. So what I mean here is our customers want to define multi-day, multi-message, multi-channel strategies for their users. And we have a product called Canvas that lets us do that. So an example of this is you've probably seen this type of messaging yourself. Let's say you sign up for a service on day 1, you get an email, then you get an email on day 3, on day 7, day 14, day 21, et cetera. That's the same type of thing I'm talking about here. It's a multi-day, multi-message strategy. So our customers do this using Canvas, which is essentially like a visual workflow building tool. You can see some screenshots of it here. It has these different branches off of here. And the nomenclature I'm going to refer to when I talk about how this works is essentially the steps, which are each of the messages, and then branches. And with branches, what that is, it allows our customers to branch their logic based on what's going on with the user. So as a simple example, Let's say that I wanted to run a strategy where on day 1, someone signs up, I send them an email. Then what I want to do is 2 days later on day 3, if they haven't used some feature set, I want to branch off that and send them an email letting them know about some cool functionality they're missing out on. But if they have used that feature, I want to branch off that, and on day 3, I want to tell them to invite their friends. So that would be 2 branches off of 1 step. The way Canvas is architected is it's extremely event-driven. It's actually entirely event-driven. In our system at Braze, every time a message is sent, an email or a push notification, we fire an internal event in our system that says that some user received the campaign. And we have lots of processes that are then listening for these types of messages. And when they capture one, they'll see if then the user is supposed to receive a message down the line. So if I get that day 1 welcome email, other processes might be listening and say, well, look, there's 2 other branches that are going to run 2 days from now, one if John used some feature, and one if John hasn't used some feature. And we're going to schedule jobs in our job queue in order to run those 2 days later. Now, we use Redis for our job queue. Are there folks here who also use Redis for your job queue? I know at least Spotify or Shopify, so you'll get that in the next talk that Mo's about to give, which is going to be exciting. But Redis has some great data sets for doing things in the future. One is the sorted set. So we store jobs that should run in the future in a sorted set where the score is the time it should run in a Unix timestamp, and then the element is the payload that should run. It's a very common pattern. You'll see this with third-party libraries like Rescue or Sidekick. It's all very similar. Now, the way that this works to fetch a job is that worker servers will then pull this set and use zRange by score to find the leftmost object on it, going from -infinity to now, and get that from the set. If they find something there, then they'll zrem it to remove it from the set and enqueue it. Now, in terms of Redis's runtime operations here, zRange by score is typically logarithmic, but because of its implementation, it's actually O of 1 for us to just get that leftmost element. But the zrem is logarithmic in order to replace the sort. And so each time we have Canvas enqueuing something, it's going to put a couple of different jobs on the set. Now, once a job runs, we have multiple different branches, and we need to control concurrency and ensure that you don't get both emails on day 3. So at the start of each branch, if we figure out if you're eligible to actually receive it, we're going to use another lock with that set NXEX to exclusively take a lockout of processing for that user. So this architecture was great, and it worked really well in staging. We put it into production. Everything was working totally fine. We were very happy. Our customers were really happy. And then one day, about 2 years ago in January, one of our customers launched what was the biggest Canvas to date. It had 11 branches and 10 million users that were going through it. And they set it to run like the next day at 10 a.m. So what this meant was that we were going to dump 110 million jobs into our scheduled set that we then needed to run through and process. And this is where things went really, really badly. Because what we had 110 million things in the scheduled set, all set to run at the exact same time. So now we have all of our processes zRange by scoring and then trying to zrem. And all these processes are doing it, getting the same element. Only one of them wins that zrem. And it becomes very slow for us to now move things from the sorted set into queues. We again have a stampeding herd issue where all of our processes are trying to do the same thing. Now what's challenging again is zrem has that O of log n runtime. And so Redis actually slows down. Even if you could do 100,000 operations per second, that might be 100,000 O of 1 operations. That might not necessarily mean you can do 100,000 logarithmic operations every single second. So we had challenges there with how Redis was slowing down for us. Now, the problem here is that we had so many jobs all set to run at 10 a.m. that it took just incredibly long amount of time for that to even move off the schedule set into queues. It actually took over 40 minutes. So to put that in context, what it meant was it was like 10:35 in the morning. We still hadn't finished enqueuing the 10 a.m. jobs. So if you were another one of our customers that had something set to go out at 10:05 or 10:15 or 10:30, your message hasn't even been scheduled yet. It's not even running in our system. This now became a really bad customer-facing incident because we were delaying so much message sending. On top of this, once we moved all of those jobs off of the scheduled set into the queue, the next problem we had to contend with was that we now had 110 jobs and branches that needed to run, and each one of those had to take out an exclusive lock. And so we were making a lot of round trip to our database to figure out if users were eligible, to then take out the lock. we had 110 million round trips we had to make to multiple databases. So once we were able to start processing, it took us over 90 minutes in order to actually send that next level of the campaign. So as you could understand, our customer was fairly upset that they launched something at 10 a.m. and it didn't actually finish sending until well after noon. So we thought that we need to fix this architecture. So there's a couple of different inefficiencies in here. The first is that the initial code design has a new job per user branch pair. So as our customers use more sophisticated or complex canvases, it's more computation for us. And then each job also had to make these round trips multiple times. So the more branches was just harder for all the different types of processing we had to do. We had to spend more effort there. So what we decided to do was think that we could probably buffer users into Redis, because these messages would tend to go out around the same time, right? Like, the customer wanted to send these messages all at 10 a.m. to 10 million people. So we didn't need to process 110 million jobs. We just needed to process those 10 million users all at the same time. So we changed our architecture. And now, when a received campaign event is fired, so I received that day one email, instead of enqueuing 2 jobs each for those branches in the example I was giving earlier, now what we'll just do is for each substep, we'll have a Redis set, and then we'll just add my user ID into that set. And the set is keyed on the step ID as well as the timestamp at which it's supposed to run. And then we're going to flush this set periodically into its own job. So we again can use Redis locks to periodically flush something. So what we're doing is we're buffering data into a set, and every time we sadd into the set, we also set nxex in order to see if we should flush a job. And every 5 seconds or 3 seconds or so, we would flush a job to drain that set off into its own separate job there. And each of those subjobs would then do an spop 100 to grab 100 users and process them at a time. So what we wanted to do was move from 110 million jobs to really something like 1.1 million jobs. The next thing that we had to contend with, though, was still fixing that thundering herd. Because even if we did that, we were still going to have 1.1 million jobs that were all going to run at 10 a.m. So we tried to make this sorted set removal and enqueuing a lot more efficient. So the first thing that we did is we added random jitter in the microsecond precision to all of the jobs that we put into the sorted set. We essentially broke 1 second up into 1 million different pieces. And the algorithm that we wrote, which we'd modeled off of what Rescue and Sidekick use, again, Z range by score, negative infinity to now, and grab that thing off. But we looked at that and we were like, well, we also could go from the right side and Z rev range by score from time.now to negative infinity. Or we could go in the middle because we have some jitter, so we could Z range by score from some random point in the middle, or Z rev range by score from some random point in the middle. And the point here was for us to increase the probability that any process Z-rems and wins. That's what we're really trying to contend against. So we're able to increase our efficiency tremendously. Just even going from the right side makes it you twice as likely to have a Z-rem that your process is going to win. So when we did this, the results were, again, incredible. We saved over 50 gigs of RAM because we didn't have all this metadata for jobs. Instead of 110 million jobs, we ended up enqueuing about 1.4 million, so it was fairly close to a 100x improvement. And instead of taking 40 minutes to enqueue everything, we enqueued everything for that one customer in just a couple of different seconds, which was fantastic. And then because we lastly batched all the data into those 1.4 million jobs, we didn't have to make as many round trips for grabbing locks or checking user state. We were able to process everything and send the entire canvas out in 14 minutes, as opposed to the 90 minutes it took for us to do that. So just want to recap here. I've talked about a lot of different things, but the themes of what I have here is using Redis to essentially control concurrency and batch and use locks a lot. So we use this pattern everywhere at Braze. We have a lot of things where we're running a distributed system. We have thousands of processes. And using set nxex is a huge value for us to be able to control the rate or the frequency that we want things to occur. And then lastly, we also buffer a lot of high throughput data so that we can process it in more of a batch nature, even though it's still happening very fast. You can process a batch every 1 second and just have queued up a lot of users since then. And this has allowed us to be much more efficient with round trips and our processing overall, and it's just made Canvas architecture much more valuable. So if there's anything I said is very interesting to you, we are hiring, so feel free to take a look at that. also have some code samples up on my GitHub that really go into detail on how that refresh ahead caching works. There's a client there that operates, it's written in Ruby, that operates that refresh ahead caching, and you can just plug that into your own systems and start taking advantage of it today. So with that, thank you all so much.